Hello students, myself Anmol Jain in Department of Information Technology at AKGEC Engineering College. Today we are going to discuss an important topic of the memory unit, that this is the memory address map and memory interconnections. So before going to the memory address map, we will learn the basics of the memory, that what is the memory and what are the different type of memories. So first we have the main memory, right? So it acts as the central storage unit in a computer system, and this is relatively large and fast memory. It is used to store programs and data during runtime in operations, right? So it is used to store program and data both. This semiconductor indicated circuits are of two types, RAM and ROM. Main memory may be of two types, this may be RAM and ROM. RAM stands for random access memory and ROM stands for the read only memory. RAM also is known as the read oblique write memory, right? Read oblique write memory, right? But if we talk about the access, both are random. Even the ROM is also the random access, but just to distinguish, we denote it with the read only memory. So the RAM chip are available in a variety of sizes. The important word is the size of a RAM, and they are used as per the system requirement. As we know that in market we are available, we are having different type of RAMs that are available in the market. That is, as per our requirement, we can purchase them. So the following block diagram demonstrates the chip interconnection of 128x8 RAM. So important thing is that is the size of a memory. So the size of the memory is represented by in this way, that is 128 into 8, right? So meaning of 128 into 8 is 128. It represents the number of memory locations. That means how many words can be accommodated, and here 8 is the number of bits in each word, number of bits in each word or location. That means how many bits can be accommodated at a location. So this is an important term, that how we write the memory size, right? So this is always written into the form of 120 m into n, where m is number of memory location and n is the size of the word, right? So this is the block diagram of the RAM. It contains number of pins. First is the chip select 1, second is the chip select 2, that is in complement mode. Next pin is the read mode, next is the write mode, and for 128x8 there are 7 address lines. So 7-bit addresses are required. So important question arises here, that how many address lines are required for a memory chip. So this can be easily calculated with the help of 2 raised to the power n, right? So if there are 128 address lines, 128 addresses, then number of address lines are required, that is 2 to the power 7. That means n equals to 7. N equals to 7 means that 7 bits are required to represent the address, right? Similarly, this 8 represent the data lines. 8 represent this data lines. So generally students get confused that while calculating the number of address lines and data lines, they compute this 128 2 raised to the power 7 address lines. Similarly, they compute 8 2 to the power 3. So this is wrong. 2 to the power 3, or we can say that data lines are 3. So this is a wrong statement. So take care of it. So here 128 are the memory location, 8 is the baud width size, read and write chip control lines, CS1 is for RAM chip select, CS2 is for RAM chip select, address lines are 7 bits. So this is the whole block diagram of the RAM, right? Sometimes it is asked that how many pins in a RAM of size 128 into 8. Total number of pins. So total number of pins will be 1 pin, 2 pin, 3 pin, 4 pin plus 7, that is 4 plus 7, 11, and 8 data lines. So here is the data bits, that is a 8 bit. So 7, 11 plus 8, 19 pins. Total 19 pins are required for this IC. So you can say one more thing here, that the data bits is bidirectional. That means the data can be read with the help of this chip or memory, and the data can be write also in this memory unit. So the data lines are bidirectional. Second is the ROM chip, that is the read only memory. So this is used for keeping programs and data that are permanently resident in the computer. This is used to storing an initial program that is called a bootstrap loader. This is the block diagram of the ROM. For example, this is a ROM of size 512 into 8, right? Again, this 512 represents number of addresses and this 8 represents number of data lines. So every time we have to calculate the number of address lines or the number of data lines for a RAM chip. So these are the 512 is the number of addresses. So number of address lines or we can say bits, that will be 2 raised to the power 9, because 2 raised to the power 9 makes 512. 2 to the 4, 2 the 8, 16, 32, 64, 128, 256 and 512. So total 9 bits are required to address this ROM, and number of data lines are 8. So this should be clear, that how many address lines are required and how many data lines are required for designing any memory chip. So we can say that 512 memory location, 8-bit word size, CS1 is for RAM chip select, CS2 is for RAM chip select. Important thing, if we compare with the RAM block diagram and the ROM block diagram, here we are having the read and write pins, but here we don't have any read and write pins, because there is no choice of the read and write. There is no choice of the read and write. It has only the one option, that is write, right? Second change is that it is a unidirectional data bus. It is having only unidirectional data bus. That means data can be read only, that we cannot write. So there is no such direction in this RAM chip. So these are the two basic differences between the RAM chip and ROM chip. So till now what we have learned, or we should understand the difference between the RAM chip and ROM chip in its block diagram. Second thing, how many address lines are required and how many data lines are required. So don't be confused for this. Sometimes a student get mistakes or write mistakes, that they multiply the 512 into 8, right? For example, they write this 8 to the 16, 8 1 the 1, 9. So this is a wrong. We cannot write the size in this way. The right way of writing the size is number of address lines, number of addresses into number of data lines. So this is wrong, right? So take care of it. Now we are having a problem that we need to design a big size of RAM with the help of a small size of RAMs. That we are having a small size of RAMs and we want to design a large size of RAM. For example, we are having the RAM chips that is of size 128 bytes, right? And we are having a ROM chip that is size of 512, right? 128 bytes RAM is available, 512 bytes ROM is available, but my purpose is I want to design a RAM of size 512 bytes, right, and 512 bytes of ROM. I am having a smaller size of RAM, but I want to design a larger size of RAM. So how we can interconnect them so they can work for a large size of RAM, right? So for making such type of memory interconnection, we need the number of address lines and number of data lines, right? So take an example here, how we will find that how many RAM chips are required to make a 512 byte while we are having available 128. So number of RAMs required equals to 512, that is the required size, upon available size, that is 128 into 8. Required size upon what size is required upon available. So required is 512 bytes and available is 128. So we can easily compute that 4 RAM are required of size 128 cross 8, right? Second thing, that number of address lines required to design 128 bytes. Number of address lines, number of data lines. If the size is 128 cross 8, so it should be on tips. If the size is 128 cross 8, then number of address lines is 7 bits and number of data lines is 8, and we want to make this size as 512 into 8, that is byte. 512 bytes means 512 into 8. We can also write it like this, 512 into 8. So number of address lines required for 512, that is 9, and data lines are 8. So this calculation should be in our mind always, that how many address lines are available and how many address lines are required to design the memory chip. So what we see here, the number of address lines are required, that is 9. So the difference between the available and required, difference between available and required address lines equals to, that is 9 minus 7 equals to 2. So there is a difference of 2. So this 2 suggests that what should be the size of the decoder to interconnect. This two numbers suggest that size of the decoder. That is a question that is asked in the question paper, and what should be the size of the decoder. So here we can compute easily the difference of the address lines between the required and available, right? So let's see that how we can interconnect them, right? So here we are having, that is 128 into 8 RAM that is available, and 512 into 8, that is RAM is available. For this purpose we need 7-bit address. For ROM we need 9-bit address. Now how many RAMs are required, that we have calculated, that we required 4 RAMs, 1, 2, 3 and 4, right? And how many ROMs are required, that is 512 bytes of ROM, and available is also is 512 byte. So only one ROM is required, right? So now here comes that what will be the memory address map if we connect 4 RAMs, right? The size of one RAM is 128 and we want to make a RAM of 512 size, right. So, first RAM that will be containing the address from these are available in hexadecimal form, but we can also compute it into the decimal form. So, RAM 1 that will be having the address from 0 to 127, right. It can be converted into the hexadecimal form. Next RAM that will contain the address from 128 to 255, next RAM 256 to 383, next RAM 383 to 511. So, total addresses 0 to 511 will be divided into 4 different RAMs, RAM 1, 2, 3 and 4, and the last RAM that is single, that is having all the addresses from 000 to 0011 F, 01 FF. Total addresses 512, 0 to 511 addresses will be available in ROM, right. So, let us see that how we design these RAMs. So, important thing is that is the memory address map, that which RAM will be selected. This will be decided by the bit number 8 and 9, because these 9 bits are required for 512 addresses. But out of these 9 bits, these 2 bits, last 2 bits, MSB bits, will decide the choice of RAM. That is the choice of RAM. That means if the combination is 00, then RAM 1 will be selected. If the combination is 01, RAM 2 will be selected. If it is 10, RAM 3 will be selected. If it is 11, then RAM 4 will be selected, right. One more address line which we have added here, that is the address line number 10. So, this address line 10 will distinguish between the selection of RAM versus ROM. So, the line 10, address bit 10 is 0 if we are interested in selection of RAM, right, and this address bit will be 1 if we are selecting ROM. So, this will be the selection of the ROM, right, and this at this condition, this is the don't care, whatever be the value of the bit number 8 and 9, there is no choice, there is no harm that what is the combination of this 8 and 9 bit in case of ROM. So, in this way we can design the memory unit of larger size. Let us see, here we are having the 4 RAMs, RAM 1, RAM 2, RAM 3 and RAM 4, and each RAM size is 128 cross 8, 128 cross 8, 120 cross 8 and one ROM of size 512 into 8. So, we required 4 RAMs, 1, 2, 3 and 4 and one ROM, that is 512 into 8. Now, we are having this CPU, right. So, how many address lines are required to design a 512 size RAM? Answer is 512 0 to 9, right, 1 to 7 and 8, 9, total 9 bits are required. So, what is to be clear, that each RAM requires 7 bits, that will be common. So, here what we have done, that these 1 to 7 bits are connected to each address lines. These are the 7 address lines that are common to each. So this question is asked that how many address lines will be common. So the answer is the 7 address lines are common to each, right? Because these 7 address lines common are because each RAM is required 7 bits. Each single RAM is required 7 bits. So these 7 lines are common. Now important thing is that at a time which RAM will be selected, because there will be an address. If there is an address, that address will lie either the RAM 1, 2, 3 or 4. So which RAM will be selected? This selection will be done on the basis of bit number 8 and 9. What is the combination of this 8 and 9? So these two bits will select that which RAM will be selected, and this task will be done with the help of the decoder. So decoder will decode that which RAM will be selected. So here if bit number 8 and 9 are 0 0, then the decoder will select 0. Decoder will select 0, that means chip select 1 will be selected. If bit number 8 and 9 are 0 1, then decoder will select 1, then RAM 1 will be selected. Similarly 1 0 2, RAM 2 will be selected, and similarly if it is 1 1, RAM 3 will be selected, right? So in this way these two digits decide that which RAM will be selected. Now one more bit is here, that is the bit number 10. So the bit number 10 is basically required to distinguish between the choice of RAM and ROM. If this bit 10 is 0, bit 10 is 0, we have seen here. If this bit 10 is 0, there will be choice of RAM. If it is 1, then there will be choice of ROM. So if this is 0, you can see if this is 0, then ROM will be if it is 0, then RAM will be selected, and if it is 1, then ROM will be selected, right? So in this way we can put all the RAM and ROM interconnected. So the question arises here are that number of RAMs required, what should be the size of common address lines, and what size of the decoder is required to interconnect all these RAM and ROM, right? So we move further. There is an example in Morris Mano that how many 128x8 RAMs are required to provide a memory size of 2048 bytes. So we have seen that the number of RAMs required equals to required size upon available size. So what is the required size? That is 2048 into 8. This is byte, right? And available size is 128 cross 8, right? So we can put it into 2 to the power 11 upon 2 to the power 7, that is 2 to the power 4, that means 8 RAM chips are required to design. 8 RAMs are required to design of 2048 byte size, right. Second question, 2 to the power 48, sorry, this is 2 to the power 4a, that is 16 RAMs are required. 2 to the power 4 means 16 RAMs are required to design 2048 size. Next is, how many lines of address bus must be used to access 2048 bytes? So, number of address lines, that is 2 to the power 12, because 2048 addresses can be written in the form of 2 to the power 12. So, 12 address lines, 12 address lines are required. And how many of these lines will be common to all chips? So, common to all chips depend on the available size. Available size is 128 cross 8. So, it requires how many lines? 128, that is 2 to the power 7. So, 7 address lines will be common. 7 address lines will be common, right. So, in this way we can compute the total number of address lines. How many address lines will be common? It depends on the input or the available size of the RAM, because each RAM is of 128 into 8. So, each RAM requires 7 bits to address its location. Next is, how many lines must be decoded for the chip select? So, number of lines required for decoder, number of lines required for decoder is equal to the difference between address lines, difference between address lines of required and available memory size. So, this is a very common concept, that is 12, that is required, available is 7. So, that is sorry, this is 2048. So, number of address lines required is 2 to the power 11, right, right, 2 to the power 11. So, 11 minus 7, that is equals to 4. So, size of the decoder, four into 2 to the power 4, that is 4 into 16 size of decoder is required. So, in this way we can compute the number of address lines, number of data lines, number of address lines required to design the higher size of memory, and how many bits are required for the decoder, and what should be the size of the decoder, right. So, I just repeat one again, right. So, if there is any doubt, you can contact to me at Jan Anmol @akgec.ac.in, right. Thank you.